If you're watching this video, odds are it's because you were referred to it by this document. And I provide the solutions with this as I posted it on Blackboard, but I thought it'd be nice to go through it, show you step by step, and maybe elaborate on some of the answers a little bit. All right? So let's do that. I'm just going to go through these one at a time, and they're divided into sections. Some of them are algebra problems. There's some trigonometry in there, but they're all prerequisites for calculus. All right? Now this document here, this is not every single thing that you need to know to begin learning calculus, because you just do the math. You took algebra and pre-calculus in order to take calculus. And for each of those classes probably met twice a week for 2 hours for an entire semester, 16 weeks. And so there's no way that this one document is going to cover all that stuff. It's just not possible. But if you need to refresh your thinking a little bit and you need to prime the pump to get ready to do calculus, this is, I think, a pretty good place to start. All right? So I'm going to go through this. All right? So here goes. For the problems under section 1, let's start with the first one. It says, use the laws of exponents to simplify. Now there are many laws of exponents, but one of them is that exponents distribute over multiplication or division. And so what that would mean for this problem is that everything in there gets this power applied to it. All right? So I think it's probably fairly straightforward. Like the 2 gets the 5th power, the x gets the 5th power, and the y squared gets the 5th power. What that's going to look like is this. 2 to the 5th power, x to the 5th power, and then like this last thing, y squared, it gets the 5th power also. All right? So the first two of these, no big deal. 2 to the 5th power, you just do the math. That's going to be 32. X to the 5th power, not knowing what the x is just some unspecified number. It's what you might call a variable. It's an unknown. I can't tell you anything else about that. But what about y squared to the 5th power? Well, there's another law of exponents for that. Y squared to the 5th power is going to be y to the 10th power. And the reason I get that is because it's what you do in this case is you multiply the exponents. All right? Okay, so then that's as far as we can take it. 32, x to the 5th, y to the 10th. If there was more that we could do to simplify that or reduce it or perhaps turn it into something else, then we would do that, but this is the end of the road for that one. All right? I will explain a little bit about this rule right here, about how when you raise a number to a power, then to another power, you multiply the powers. I might explain a little bit about that. I'll give a little proof. I think if you're learning to do some math, you should, as best you can, understand why the rules are the way they are. I'll give you another example. What should x squared to the 3rd power be? According to the rule I explained up here, it should be x to the 6th power. Why is that? Well, think about it. Exponents are repeated multiplication. So this means that is multiplied by itself 3 times. But what is x squared? Well, x squared is x times x. Multiply x by itself, 2 x's. All right? And then, well, how many x's? What is this? X times x times x times x times x. Well, there are 6 of them, all multiplied together. That's otherwise known as x to the 6th power. So, you know, there's some insight to the reason why this rule works the way it is. Anytime we raise a number to a power and then a subsequent power, we could just multiply those powers together. All right, so I did the example. I'd like to prove as much as I can the reason for the way it works. Okay, now let's do the next one. So 2 things going on here. This is distributing, right? the fact that this is x plus x squared, two terms, times this 1 with the parentheses, it means this one term, this one item, multiplies everything that's in there. All right? Okay, so this will be x to the 9th times x plus x to the 9 times x squared. All right? Now about this, what's x to the 9th times x to the 1st? So this is x times itself 9 times, and then there's another one that makes 10. Okay, and then x times itself 9 times, then times another 2. That would make 11, right? Okay, so that's what each of these are if you multiply them. So let's see, x to the 9 times x, that's x to the 10th power, and then plus x to the 11th power, x to the 9 times x squared. All right, now can I add these together? No, they're not like terms. Can I cancel anything? I can't do that. I don't have any more options once I get to this point. All right, so I distribute, but then when we multiply like things, we add the exponents. See, 9 plus 1 is 10. 9 plus 2 is 11. That's not how I was thinking about it when I worked it out. I said there's 9 here, and then there's another one that makes 10. There's 9 here, and there's 2 more that makes 11. But we could say, all right, well, here's the rule. X to the n power times x to the m power. These being like things multiplied together, the power will be n plus m. Okay, multiply like things, add the exponents. So there goes question B. Let's look at C. So for this one, I would like to take it apart a little bit. Okay, let me show you what I mean by that. Maybe we would rather see this as 60 divided by 4 times x to the 5th divided by x times y squared divided by y squared. All right. So that's what I'm calling that taking it apart. What was the reasoning for that, or is that fair? Is it playing by the rules? Well, here I'm writing this as 1, 2, 3 fractions multiplied together. How do you multiply fractions together? Straight across. If I were to multiply these 3 fractions together, it'd be 60 times x to the 5th times y squared. That's what we got here. Divided by 4 times x times y squared. That's what I've got there. But I thought, rather than leave it together, I'll take it apart so that we don't get distracted. We can, one part at a time, figure out what we're supposed to get. Like, you could say, what is 60 divided by 4? That's 15. And that way, we're not looking at the other stuff. We could say, what's x to the 5th divided by x? Well, okay, let's see. X to the 5th. Isn't this x to the 5th right there? X times itself 5 times. Divide by 1x. This is x to the 5th divided by x. What's that leave you after canceling? X to the 4th. Okay? X to the 4th. So then when we do this part, we're not looking at the rest of it. We're just seeing that. What about this last part? Y squared over y squared. That's 1. Those just cancel. So it's just 15 times x to the 4th. All right? That's as far as I can take. That'll be my final answer. Now, so in this part right here, I thought I'd break that apart this way, you see, and figure out that it's x to the 4th. But there's a rule for that too, all right? If you don't want to think about it like me, I'm trying to show you a way that is undeniable, all right? But what's the rule behind this say? If you divide like things, like say you divide x to the n power over x to the m power, the rule is that when you divide like things, you subtract the exponents. The power would be n minus m, all right? Okay, is that consistent with this? What should x to the 5th power over x to the 1st power be? X to the 5 minus 1 power. That's 4, all right? Okay, now, you have to do this like me. Now, I mean, you might say I'm overthinking and I'm showing too much detail. But, I'm considering that's my audience right now. They want to see a lot of detail, different explanations, and you can take away from it what you want, all right? Okay, so let's go down to this one. Y to the minus 2 over y to the minus 8. Well, I could say that falls under this, doesn't it? When you divide like things, you subtract the exponents. It doesn't really matter what those exponents are. 5 and 1 are pretty simple. Negative exponents, that means something a little bit different, but the rule is not different. Okay, so I'll use this rule right here. Now, just according to the rule, it's going to be this, right? Divide like things, subtract exponents in that manner. Well, here you go. But then that's y to, what's negative 2 minus negative 8? Negative 2 plus 8, and that's going to be a 6, y to the 6th power. That's all it is, y to the 6th power. Okay. Now, again, that's might be enough for you. I don't know. But I think, whether this is easy for you or whether you feel like you're learning something new, you will probably need to have some flexibility in how you think about things. And what I mean is, if you're going to do calculus, you can't be stuck on just one way of thinking. You might have to get a little bit creative and learn another perspective. So is there another way I could do this one? How about this? I could see this as y to the negative 2 over 1 times 1 over y to the negative 8 power. Okay. All right. So again, what's the rationale? Well, when you multiply fractions, you multiply straight across. So these would multiply to be that. So it's consistent. But then again, what do negative exponents mean? Y to the negative 2 power could be otherwise understood to be this. That's the meaning of a negative exponent. And y to the minus 8 power could be understood to mean this. Okay, that's also the meaning of a negative exponent. Okay, that's what these two individually become. But what is this? This is a y to the 8th over a y squared. If you wrote it out like this, 8 over 2, there would be 6 after you canceled. If you saw it as I'm multiplying or I'm dividing like things, I'll subtract the exponents. 8 minus 2 is 6. See? I mean, I got there a totally different way, but, like I told you, I want to encourage you to be a little bit flexible in how you see things. Both these breakdowns, both techniques are all according to the rules. All right, we got to learn the rules. Okay, so let's do this one real quick. And I think I would like to more or less stick with that same initial step. Like, I'm going to see this as a 4 over a 1, an x over an x to the minus 2, and a 1 over y to the minus 5. I'm going to look at it like that. What if I multiply all this back together? Well, I'll get this, so it's okay. I just want to separate it where the like things are together. The 4, the number, the x's, and the y's. So I got a 4 over a 1. That's just going to be 4. What would this be? That's that situation where you subtract the exponents, right? Like that. And what about this? Well, I mean, there's nothing to cancel and there's nothing to subtract like over there, but I could say that 1 over y to the minus 5 power is just y to the 5th. That's what negative exponents mean, so I can do that. Well, what am I going to get then? 4, okay. 1 minus negative 2, that's 1 plus 2, that's 3, so x to the 3rd power, and then y to the 5th. All right. So then I'm using the same rules, but I'm trying to be flexible about it. All right. Okay. All right, now this one. Here for the first time we see a root, okay? And there is a rule for that too. Here's what the rule says. We could write it something like this. Fractional powers are convertible to roots. like that. Okay? I'll try to prove that to you real quick. Like take 9 to the 1 over 2 power. Okay, a fractional power on the 9. According to this, that would be the same thing as the square root of 9 to the first power. All right? And I figure, well, why not? I'll prove that to you. I'll, as much as I can, give you a reason to believe that. I don't want you to just accept it. If you have some reason to know it's true, it'll mean a lot more to you. I think it'll be easier to remember. So let's see, what's 9 to the 1/2 power? We'll trust the calculator for now. It's going to be 3. Okay. And what's the square root of 9? Well, we ought to know that, but I'll pretend we don't. Square root of 9, also 3. So, does this give you some confidence in that? Or does this give you a basis to understand it? I hope so. All right. So let's use this as a basis for getting started up here. This would be x over, you remember those rules we were using? They deal with exponents. In the heading of the question, use the laws of exponents. So I want to see this as an exponent. I want to have that flexibility. All right? I don't have to see it as an exponent, but I think it might allow me to do something with this. All right, so I wrote this that way. And then what was the rule we saw a minute ago about dividing like things? When you divide like things, you subtract the exponents. All right, the exponent up there is 1. 1 minus 1/2 is 1/2. Okay, so you could give this as the answer if you want to. Or, just depending on what you needed to do or how it was desirable to see the answer, you could write it that way. They're the same thing, right? Okay, but nonetheless, we can simplify that to that. So for these are similar enough. I think I'll just do H. On the document you'll have the answers to both of them. But let's take this one and say, okay, here's what I got here. This is y to the 3 over 2 power, all according to that. And this is just y to the first power. Okay. So once divided, what was the rule? Subtract. So this is y. So 3 over 2 minus 1. 3 over 2 minus 2 over 2 is 1 over 2. So we could say y to the 1/2 power. And as far as an answer goes, that's a perfectly good answer. But if need be, if needed or desired, we could write the answer like that. Okay. All right. Now this one does look, I think, just comparably more different than the rest of them. But I want to put it in the same context. So let's say like we want to look at this problem like the others. I want to look at it like, where was it? When you multiply like things, yeah, you add the exponents. I want to see it like that if I can. And I think that's possible. So this is x plus y to the first power. And what should we say about that? That's also x plus y to a power, right? A fractional power, a power of 1/2. So this is x plus y to the 1/2 power. Now, I'll have you look at that. Why would that be any different than x to the 9th times x squared? It wouldn't. This thing here is the same as that over there. So we add the exponents then. What's 1 plus 1/2? It's 3 over 2. So you could say x plus y to the 3 over 2 power. All right. Okay, is there another way to do it? Yeah, fractional powers do convert to roots, so we could say the square root of x plus y to the 3rd power. But these would be the same thing, the square root and the 3rd power, all right? We got to be flexible. We should be aware that both of those mean the same thing. Okay. All right, on to the next one then. So this, what you saw so far, that takes care of everything under question 1. All right. Look at question 2. Right, here's question 2. Multiplying. All right, multiplying is another story. There's a procedure or a rule for everything. And if I was going to multiply, I guess the terminology here is that's a binomial. It has 2 terms in it. Times another binomial. Also has 2 terms in it. Okay, so if you're going to do that, you multiply 2 binomials. The procedure is FOIL. All right, it means first, outside, inside, last. There's an order to how we multiply the terms. So the first would be 2x times 4, 8x. The outside, 2x times x, or 2x times negative x, negative 2x squared. Okay, and then negative 1 times 4, and then negative 1 times negative x. Okay, so look at this and look at that, and just make sure that now or sometime you can tell the pattern that unites these. The first times the outsides times the insides times the last. That's the procedure. That's how you do it. Not the only way to do it, but it's what everybody learns. Okay? So to present this into some kind of final answer, I think probably some rearrangements in order. Let me write the highest exponent term first. Let me combine any like terms, 8x and x. Those do combine. 8x's plus 1 more x gives you 9x's. And then negative 4. That's the only thing that's left that's not combinable with anything else out there. Here we go. Okay, if we could do more with it, we could, but we can't. Now, I put these together just hoping that you'd see, well, there's a similarity and a difference to A and B. Here's people will have the temptation to say, the way you do this is that gets squared and this gets squared also. So let's say, well, you get to 2x and you square it, then you got the minus and the 3 and you square that. And that's tempting, but like a lot of things that are tempting, it's not right, okay? You do this one like you do that one. That would be the right way. And what I mean by that is that to square something is to multiply it by itself. Okay. So there. And then we know how to do that, right? That was covered up there. It's going to be 4x squared, okay, minus 12x. Once you do like negative 6 and negative 6, and then plus 9, all right? So it's not like those are different, but I just needed to, I needed you to see that we need to start this one off in a way that allows us to do it like that one. And we're definitely not going to do this, okay? Like, it's not right. Now, I feel like that when we do math and we just have X and Y and A, B, C, and we use the alphabet, it's just not very tangible, all right? So I'll try to prove this thing. I'll try to prove that that's wrong, okay? Think about it like this. Is 9 plus 2 squared equal to 9 squared plus 2 squared? If you were inclined to do this problem that way, that would be like believing that this was true. Is it? Well, let's see. What's 9 plus 2? It's 11. Okay. What's 11 squared? Happens to be 121. Let's look at the other side. I mean, if you were going to do this, it's like saying this number is equal to that one. What's this? 81? What's this? 4? Is 81 plus 4 equal to 121? 81 plus 4 is not even close to 121. Okay? So, question mark, is that right? No. Okay? And you can look, I mean, if you want to, you can look at things like this. You know, if this doesn't make sense to you, if the rules seem arbitrary, try it with numbers, and it won't. 121 is just not equal to 85. It's not right. Therefore, this is not a correct way of breaking that down. Okay. All right, so that's why I showed you that, but I scratched it out. All right, what about this one? Okay, well, here, like, I guess the FOIL procedure wouldn't apply to this, but it's not really that big of a deal. This has 3 terms in it, that has 2. I guess all that's got to happen when you multiply this stuff together is that every one of these multiplies every one of those. Okay? That's all you do. So, in other words, like x squared multiplies both of those. Then x multiplies both of those. And so on and so on. Okay, so let's do that. X squared times x. X to the third power. X squared times negative 1. Negative x. Okay? X. Now multiply this times both of those. X times x. X squared. X times negative 1. Negative x. Oh, whoops. So x squared times x. X third. X squared times negative 1. Negative x squared. All right. I caught that. X times x. X squared. X times negative 1. Negative x. Now 1. 1 times both of those. 1 times x. X. 1 times negative 1. Negative 1. So everything in there, one at a time, multiplied everything in here. And this is what we got. What's left? X to the third power. Those two cancel. These two cancel. Minus 1. All right. Turns out you could do FOIL like that. It's everything in here multiplies everything in there. You could do it just like this one, but everybody learns FOIL, so that's the way I explain these. And I told you something a little bit different, but it's really the same thing for that one. All right. Okay. So let's talk about the next 3 factoring real quick. There's a technique to factor every problem. For this one, we're looking for, think of it like this. Factoring is the reverse of multiplication. What 2 things would you multiply in order to get that? I feel like we kind of saw that already when we did these, right? It's like I could look at this like, if I multiply those, I get this. But it's possible to work backwards from here to get there. I mean, if you can go one way, you can go the other. So I'm thinking about this one that way. What do you multiply to get this? Well, first, I think you'd need x times x to get x squared. All right? Okay, that's probably the easiest thing to accept about this. What about the rest of it? Well, here's the trick for this kind of problem. I need to think of 2 numbers that multiply to get you positive 7, but simultaneously add to get you negative 8. Can you think of 2 numbers that multiply to be negative, or multiply to be 7 and add to be negative 8? How about negative 7 and negative 1? They do it. Negative 7 times negative 1 is 7. Negative 7 plus negative 1 is negative 8. All right, now that alone is definitive that this is right. Now, of course, you can check it. We just learned how to multiply. I mean, you should know how to check it. You should know how to assure yourself that the answer is right. If this is right, when I multiply it out, I should get that over there. So there's really no reason to have any doubt about it. Let's see. Okay, x times x, x squared. X times negative 1, negative x. Negative 7 times x, negative 7x. Negative 7 times negative 1, positive 7. Is that going to do it? I got an x squared. In the middle there is negative 8x, and there's a 7. All right? Which, yeah, who knows? If you didn't know this trick, you could have figured that out by trial and error and checked it until you got it right. Okay? All right, so that's how we do one like this, like a trinomial. If it's 1x squared, a number x, and a number. What about this? This is a different pattern, okay? This is called the difference of 2 squares, and I guess the way people normally give the pattern is something like x squared minus y squared. We'll factor as x plus y, x minus y, okay? A difference of 2 perfect squares. That's what this is. Why is that? Well, this is 9 squared minus a squared. Okay, 9 squared minus a squared. All right, well, there's your template, right? That's what this is. So it should factor this way. 9 plus a, 9 minus a. Okay. Every now and then we see that kind of thing, and this is how we factor it. You could check this one like you did the other one. Why not? Okay.